So now that we know how to solve equations by completing the square, the question you might be asking yourself is, well, why do we need completing the square at all? I mean, if we have factoring, we have the quadratic formula that always works for us, why would I ever need to complete the square? And the answer is, well, it can help us a lot whenever we are graphing. And so as a little bit of motivation, we're going to take a look at parabolas and how completing the square can help us with that. So we're going to jump over to GeoGebra and remind ourselves a little bit about how to graph parabolas. So let's just start with our basic parent function here. So what I'm going to do is I'm going to graph the function f of x equals and then just x squared. All right, so that's my function f of x equals x squared. It's a parabola. The most basic version of it, my vertex is at 0, 0. No big deal. So the question is, how can I manipulate this? How can I change this to still be a parabola but look slightly different? So what if we instead graphed a function like x squared plus x squared and then plus 1? So how should that change it? So without actually putting it in yet, so let's think what's going to happen here. My function still has x squared in it. It's just that now every function value that I get out, what I'm going to do is I'm going to add 1 to whatever the value was before. So whenever I add 1, it actually takes my entire parabola and just shifts it up by 1. So now my vertex is at the point 0, 1, but everything else is exactly the same. Everything has just been shifted up by 1 point. And so as you can imagine, I could do different things, like I can add 2, or I can add 3, I can add 4, and it keeps moving up, or I could even subtract 1 or subtract 2, and it would move it down and so on, right? So the question is, though, how can I shift it left or right? And so these are just different transformations of my function. And so if I add or subtract something after the function's actually already been done, the squaring has been done, it just shifts it left and right. If I want to, up and down. If I want to shift it left or right, I have to do something to x before the function actually occurs. And so what I can do instead is, if I take my x value and before I square it, let's say that I subtract 1 this time, what I will get is a shift to the right. The way that I think about this is that I'm taking my values, I'm plugging them in for x, but everything's going to happen 1 later than what it did before because I'm subtracting 1 from my x value. And so if I change this to, I could shift this over by 2 or by 3 or by 4, or I could go the other way. I could add 1, and now everything is shifted over to the left because everything is occurring 1 unit earlier than it would have before. Because before, when I had my x squared function, if I plugged in 1, I got out 1. Now if I plug in 1, it's actually like I'm plugging in 2 because I'm squaring 2 then. So everything's happening 1 step sooner than what it did previously. And so I could do both of these then. I could do both of these. I could both shift it to the left and to the right, and I could shift it up and down. And so what this is doing is it's changing my vertex and where my vertex is at. I could also do one more thing. I can transform in one more way, which is I could multiply it by something. So let's say I take this all and I multiply it by 2, for example. Everything now is twice as far away from the x. Oh, that's actually a bad way of saying it. Everything is twice as large as it was previously, right? So let's actually just maybe simplify this down. Simplify this down to just my parent function of x squared again. So if I multiply this by 2, what's happening is that I haven't changed when I'm adding in things, but when I multiply by 2, everything is just twice as far away from my vertex as they were previously. So let us jump back to actually formalize this a little bit. So in general, lost where I put my pen. If I have a function, so this is my parent function, so f of x is equal to x squared. The general form that I can do for this, I should probably use a different function. G of x is equal to, all right, so x minus h. This tells me how much I'm shifting it, plus k. So h tells me how much I'm shifting it left and right. K tells me how much I'm shifting it up and down. and then multiply by some a values. This tells me how much I'm stretching it or shrinking it. And so this function, this is called vertex form for my parabola. This tells me what's going on with my function way more than the general form does. The issue, of course, is that what if I'm giving something in general form? So let me just say this last part. So my vertex will always be at the value h comma k, and then my stretch here will be whatever a is. So yeah, let's say we were given something, given a function where they gave it to me in general form. So let's go with h of x is equal to ax squared plus bx plus c. This is general form. Well, that doesn't really tell me anything as it is. How can I convert it to my vertex form to learn all this information I had? And the answer is completing the square. So here's what I'm gonna do. Let's take an example here. So let's make something up. So let's say I have the function f of x is equal to 3. No, not that one. Did I have one? No, I didn't. Okay, let's just use this one. 3 times x plus, nope, that's not what I wanted. 3x squared plus 12x plus 11. Okay, so let's say I'm given something in general form like this, and I want to figure out what the vertex and the stretch is on it. So I need to convert it to my vertex form. So I'm going to go about the process of completing the square. The only issue is that now on my left-hand side of my equation, where I would want a 0 to be, I have this f of x. And that's fine because I know this function, we usually just we don't touch the left side of the function, and then we just mess with the right side. We're gonna mess with both sides here. So I'm gonna go about completing the square. Here's how I'm gonna do it. I'm gonna start off by subtracting 11 because I want to get my x values by themselves. So I'm gonna subtract 11. So this will now be f of x minus 11 is equal to 3x squared plus 12x. Okay, now I want to figure out what I can add to this to make it a perfect square. The issue is that I've got these coefficients here. I've got this 3 on my x squared. So I want to get rid of this. I want to pretend like that's not there. So what I'm going to do that is I'm going to divide everything by 3. But I have to do that to both sides. And so what I have then is f of x minus 11 over 3 is going to be equal to x squared plus 4x. Now I can go through the process of figuring out what can I add to both sides to make this a perfect square. So I'm going to ask myself that. What I'm looking like this is going to factor into is x plus 2 squared. That's my goal, I think. So what I have to add to both sides then is I have to add 4 to both sides. So this is going to be f of x. So my left side is kind of becoming a bit of a mess, but that's okay because it's like it's just storing everything for me so that I can actually do all my work on the other side. So once I have this now, so x squared plus 4x plus 4, I can factor. So this is f of x minus 11 over 3 plus 4 is equal to, all right, x plus 2, that quantity squared, and then plus, no, that's it. Okay. So now I just have to put everything back. I've done all the hard work. I've gotten this into my factored form. I just have to put everything back where it was. So I'm going to start off by subtracting by 4. So this will now be, I'm going to go up here. I'm going to start by subtracting 4. So I'll have f of x minus 11 over 3 is equal to, and then x plus 2 quantity squared minus 4. Now multiply everything by 3. F of x minus 11 equals 3x plus 2 quantity squared, and then minus 12. And then I'm going to add the 11. So this will be f of x equals, and then 3 times x plus 2 quantity squared. And then, so I'm adding 11, so minus 1. Right, so I went through this whole process of completing the square, so now I can tell all the information that I want to about this. I can tell you that the vertex of my parabola is at the point -2, 1. And then my stretch here is a stretch of 3, a vertical stretch of 3. Okay, awesome. Let's look at one more example of this, and then we'll call it a day. But yeah, I'm just using completing the square here so that I can tell a little bit more information about what's actually going on with my parabola. All right, here is another one that might be slightly more challenging. If I can just figure out where I put it, here it is. So f of x is equal to, all right, 1/2 x squared minus 4x plus 11 again. Okay, so I am going to go through the same process. I am going to subtract the 11, so f of x minus 11, so I can get my x terms by themselves, so 1/2 x squared minus 4x. I'm going to do something slightly differently here. Last time I divided by whatever my coefficient was, so in this case I divide by 1/2. I'm going to do the same thing, but just slightly different. I'm going to factor out the 1/2 just to give us a little bit different look here. We could, of course, do the same way we did last time, but this is, you know, why not, just for kicks. 1/2 times x squared. Okay, when I factor out 1/2 from -4, what I actually get is -8x. Okay. All right, so now I'm going to ask myself again, what do I have to add into x squared minus 8x so to get it to factor into a perfect square? And so what I'm thinking here is this is going to factor into x minus 4 squared. So what I have to add is 16. Okay, so here's a little bit tricky part, and this is why we don't have to do it this way, but I'm going to do it just because I think it's slightly interesting. I'm going to add 16 to this side of the equation, but I'm adding 16 inside of my my binomial here, and inside my factor part. So if I add 16 to this side, what I'm really actually doing is adding 8, because I would end up multiplying it by 1/2, right? Because if I have 1/2 times x squared minus 8x plus 16, well, when I expand this all out, what I would have gotten is 8. So what I'm going to add to the other side is 8. F of x. So that what I get is minus 3. Great. Now I can factor again. So f of x minus 3 is equal to 1/2 times x minus 4 quantity squared. And I just have to add the 3 over. So I did save myself just a little bit of time by not moving everything over. And this is just a nice little thought to have anyway. So now I can tell that my vertex for this parabola will be at the point 4, 3. And that this is a, so some people will call this, I'm still going to call this a stretch. Actually, no, I'm not. That's a lie. I'm just going to call this a shrink. What you'll hear most people say is this is called a shrink. This is a shrink of 1/2. The reason I don't like usually saying shrink is that because it's still stretching it by 1/2, which is in turn shrinking it. You know, if really you're shrinking it by a factor of 2, but that's a much longer conversation to have. Anyway, this is what's going on. So I used my completing the square to manipulate this function into something that was easier for me to use to actually be able to graph. And so even though I'm not solving for anything, and that's why, you know, factoring it or using the quadratic formula wouldn't really do me any good here. What I can tell is a whole bunch of information from this completed square form or this vertex form for my parabola. So completing the square has its uses besides just solving equations. It also helps me graph things. So now we can use that in the future, add to our toolkit.